I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about an example problem for bidirectional search process. In this case, this is the graph we have taken for analyzing the bidirectional search process. In this graph, the node A is connected to B and C, and B is connected to D and E, and C is connected to F and G, and node D is connected to H and I. Node E is connected to J and K. Node F is connected to L and M, and G is connected to N and O. So in this problem, we are considering this the goal node is that is initial node is the this A initial node. We are keeping it as this is the initial node, and we are fixing the L as the goal node, or otherwise the another name goal node, another name we are calling it as the target node. So from this graph, we are going to have the analysis for bidirectional search process. So in this case, A is the starting node and the goal node is the L, and aiming to meet at a common node. So bidirectional means we have to start from A, there is starting node and goal node, and we have to find out one common node, aiming to meet at a common node. So instead of searching from the start node all the way to the goal, bidirectional search breaks the problem into two smaller sub-problems. How? The forward search expands. The forward search and backward search will be there. The forward search expands outward from A, while the backward search move in the opposite direction. So if it is coming in this direction, and from backward search, it will go like this, backward direction, there is opposite direction from L. When two searches meet at a common node, the algorithm reconstructs the shortest path. This approach significantly reduces the number of nodes that need to be explored, making it more efficient for large graphs. So in the first iteration, initialize the searches, and at the start, the search initializes two separate processes. Forward search begins at node A, backward search begins at node L. Each search starts with only one node in its respective frontier. Since the two searches have not yet met, the next step is to explore the neighbors of these nodes. So this is the starting point, and it is not meeting. And the second iteration, expanding the nodes. We have to expand the nodes. Forward search. What is happening in the forward search? It expands node A and visits its children. The children of A are B and C. B and C. And backward search, it expands from L, moving to its parent. What is the parent of this L? And parent K. As L is the child of K. At this stage, the forward search has visited A to B and A to B and C. We'll write it as A to B, comma C. The backward search has visited L to K. Since there is no overlap between the forward and backward search frontiers, the search continues. And in the next iteration, that is iteration number 3, expanding further in the forward search from B to, we explore D and E, and F to G, C to, that is we explore D and E, and from C, F and G we are exploring. And in the backward search from K to, we explore its parent E. From E, we explore to its children I and J. Now the forward search has visited, A to B, D, E, and A to C to F, comma G. The backward search has visited L to, that is here, L, and from L to K, K to E, and from this I comma J. At this stage, there is still no meeting point, so the search is continued. So we are moving into the fourth iteration. In the forward search expands further from D to where it will go. We visit H and I, and from E we visit J and from E, J and K we are moving. From F we visit L and M. From G we visit N and O. Backward search continues from I, moving it to its parent, moving it to parent and parent B and J, moving back to E. At this stage, the forward search is A to B, D to H, comma I, and A to here B to E, I, J, and comma K, and A to in this direction, A to C to F, L, and comma M. Then A to C to G to N, comma O. So in the backward search, how it will move? L to K to E to I to, that is I comma J, then to B. So the forward search has reached L, the backward search has reached B. So there is a meeting point at B. So at this point, we observe that the forward search has reached L and the backward search has reached B, meaning that both searches have a common node B. This confirms that path exists between A and L. And now we proceed to reconstruct it. In the next step, meeting point and path reconstruction. In this case, like we are doing it. The meeting point is found at B, and we now reconstruct the path. Forward path from A to B, and backward path from B to L. Backward path. So thus the shortest path between A and L is A to B, B to A to B, B to L. The bidirectional search successfully finds the path without having to explore the entire graph, making it a highly efficient approach. So this could be explained in table also. In the forward search A and backward search L, we are doing it. What is the action? Search, start the search from A to L, and from A to B and C, and backward search L to K, and expands nodes from A to L. Similarly, A, B, C, D, E, F, G, L, from the backward search L, K, I, J expands the node from A to L. And in this case, A, B, C, D, E, F, G, H, I, J, and backward search L, K, E, I, J, B. And where it is meeting at the node B. So meeting at node B, path reconstruction starts. So the path reconstruction is A to B to L. So the complete path is A to B to L. So coming into the summary of bidirectional search, simultaneous forward and backward searches has been done. The search starts from both A and L, reducing the total number of explored nodes. Meeting at point B, instead of searching the entire graph, the searches meets in the middle at B. And efficient path reconstruction has been done in this case. Once the searches meet, the path is entirely easily reconstructed by combining the forward path A to B and B to L, backward path B to L. And significant reduction in search space is we are getting it by searching from both ends. Bidirectional search requires far fewer node expansion than the traditional unidirectional search. This method is particularly useful in large scale applications, such as large scale applications means route finding, network routing, and AI path planning, as it optimizes the search processes and reduces the computational cost. So, hope everyone understood this bidirectional search process. The remaining things we'll discuss it in the next lecture. Thank you.